All right, today we're going to be looking at applications of our trig functions involving angles. So the first example here is you are in a car of a Ferris wheel. The wheel has a radius of 8 meters and turns counterclockwise. So that'd be this direction. Draw a sketch and then graph the height of the cart that starts at the right side as it completes one revolution. Okay, so let's start with a diagram. So, for those of you who don't know, Ferris wheels, big circles. So we're going to do our best to draw a beautiful circle. And I think I have to draw mine a bit bigger because I'm going to put some labels on it. So let me try that again. Does not have to be a beautiful circle. Mine certainly is not. Pretty it up a little bit at least. All right. Okay, so circles have centers, so let's draw a dot for the center of our circle. And this circle, this Ferris wheel, has a radius of 8 meters. So to refresh your memory, a radius is this distance from the center to the outside. Diameter is twice that. So it's the distance from one edge through the center to another edge. So we have maybe we'll draw a little line here. Say this is 8 meters. Okay. And let's draw where our cart is. And I'm going to represent our cart with a dot. We could try to draw a nice pretty diagram, but usually in math we think of everything as a dot. Is at a specific point, even though a cart has volume. Okay, so it says that we start on the right side. So let's draw our cart right here. So this is our cart. This is where it starts. And we can label some other important positions. So this is where we start. And if we think about how high this is like 8 meters high, right? So the ground is at the bottom, obviously, and our Ferris wheel is 8 meters. So this would, down here would be 0 meters. This here would be 8 meters. And the top would be, 8 to the center and another 8 to the top, so 16 meters. When we come down to the left side, would be at 8 meters again. Okay, so our cart is going counterclockwise, so I'm able to draw a little arrow around our circle. And now we want to start representing these, us going around using angles. So we'll always start at 0 degrees of rotation. So at the beginning, we're at 0 degrees rotated, and we're at 8 meters height. And then we could try to represent all of the different varying angles in here. We could draw a triangle in here, a right angle triangle, and figure out the angle we've rotated and try to represent the height using SOHCAHTOA. That's absolutely possible, but we don't need to do that. Because we're going around a circle, we know we're going to get some sort of curve. And we can tell here, after we've gone 90 degrees, that's when we'll be at the top. If we continue going, we'll go 180 degrees. We'll be at 8 meters. And after another 90 degrees, when we're at 270, we'll be at 0 meters at the bottom, and then another 90 degrees, we'll be at 8. So this is 0 degrees, it's also 360 degrees. And then we would keep going around and around and around. It's generally how circles work. Okay, so let's try to graph this. So let's note our top and our bottom here. So our minimum value we need to be able to represent is 0, and the maximum we need to be able to represent is 16. So if we scroll down to our graph, we need to come up with a scale that'll work. And I think if we go up by 2s, that will work. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Don't think we need the 18, but that's fine. All right, so let's draw the height of our cart. So we can just use these numbers we found. So at 0 degrees, we should be at 8 meters height. Let's put a dot there. After 90 degrees, we'd be at 16. So 90, 16. After 180, we'd be at 8 meters. 270, we'd be at 0, so we'd be at the ground. And after 360, we would be back at 8 meters height. Okay, so what we get here is we get a wave. The shape we're familiar with here. Okay, so that kind of looks like a sine wave maybe, or a cosine wave, depending on where we're starting. This one particularly looks like a sine wave. And the next part of the question is to write an equation for the height. So let's look at this and talk about how we're going to write an equation from it. Well, let's talk about the amplitude first. So the amplitude is, well, it's the distance from the center to the top or bottom, or the maximum minus the minimum over 2. So it goes from 16 to 0. So just difference of 16 divided by 2 is 8. And you'll notice that this is also, the amplitude is also the radius of the circle. Okay, what else? Well, we have, say, the vertical displacement, or the vertical shift, which is the height of the center of our wave. So the height of our center is 8. In this specific example, it is also the radius, and that's because we're assuming this Ferris wheel is on the ground. But we'll do an example in a bit where it's not 8. It's not the same as the radius. We could also talk about the period. The period for this is 360. That will affect our k value, but if the period is 360, then the k value is 1. So we don't need to change that. Okay, so I think that's maybe enough. Maybe we need to translate left to right when we assign this a sine or a cosine. But let's think. I think a sine wave makes sense. We start at the middle and we're going upwards. If we start at the middle and went downwards, then we'd maybe have to choose negative sign or do a cosine that's been translated or something like that. But that's fine. So we can write a height function, h, is equal to our amplitude, 8, sine, there's no transformation to our period, so theta. And a sine wave, I don't think we need to translate it left or right to make it line up with the y-axis. So I think we're good. So we don't need a phase shift. Plus our vertical shift, plus 8. All right, so that is the equation for the height of the cart on the Ferris wheel. Okay, let's try another one. Okay. So there's a trick where you spin a bucket of water fast enough that the water doesn't fall out when the bucket is upside down. So you fill a bucket with water and you hold it in your hand and you spin your arm around in a circle really fast. And if you go fast enough, then the water doesn't fall out and get all over the ground. But if you go slow, then the water falls out of the bucket and gets all over the place. Okay, model the height of a bucket for a person performing this trick, where their arm is 1 meter long, their shoulder is 2 meters above the ground, and they start with their arm straight down. Okay, so let's draw a diagram so that we can model the height. Modeling is an expression that means like represent it graphically and perhaps with an equation, and later on we'll talk about the equation for this. So we have this person's shoulder and their arm, which is straight down, and their arm spins in a circle. So let's represent all that. Let's try to draw a good circle around their shoulder. That is not great. Let's try a better job myself. That's okay. Okay. So this is where the bucket is, and their shoulder is here. Now, this isn't on the ground. It says that this is at 2 meters off the ground and that their arm is 1 meter long. So when we're going to try to label some different heights on this circle, we need to take that into account. So if this is the ground, it's going to be somewhere down here. And I'm not going to try to draw the person in this diagram. It gets a little too cluttered if we do that. Okay, so this at 0 degrees, where we start, we're at 1 meter. And it doesn't tell us which direction we rotate the bucket in. But the height next is the same no matter what. If we're over here or if we're over here, it's 90 degrees. We'll just say it goes this way. It doesn't tell us, so we get to decide. Okay, so at 90 degrees, the pail would be in line with her shoulder, so at 2 meters height. After 180, it would be up here, 180 degrees. And it would be the height of their shoulder plus their arm sticking straight up with the bucket on it. So that'd be at 3 meters. And over here at 270 degrees, we would be at 2 meters again. And then we'd go around and we get to 360, back to 1 meter, and then go around and around and around. Okay. So let's try to graph this. So we need to go from 1 to 3. So I think we can fit that in with every 3 grid spaces being a mark. So 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3. Just fits. Okay. So let's start here. So we start at the bottom here. So 0. Let's choose a different color. So 0 degrees, we're at 1 meter. 90 degrees, we're at 2 meters. 180, 3 meters. 270, we're at 2 meters again. And at 360, we're at 1 meter. And we get a beautiful curve again. Okay, so that is our curve for the height of the bucket across a single revolution, single spin around. And we could keep going if we wanted to, and we could work backwards as well. That doesn't necessarily make sense in the context of the question, but we could do that. Okay, so next up we want to find an equation for this curve. So let's think about what the amplitude, the vertical shift is, and then we'll assign it a sine or a cosine. We'll also look at the period. Okay, so this has an amplitude of 1, so max minus min. We could write that out. So amplitude, remember we always have max minus min, so 3 minus 1 over 2. That's just 1. Okay. Our vertical shift is the height of the center is 2, a positive 2. So V shift is plus 2. Our period's 360 degrees. For all our angle questions, the period's going to stay the same as 360. It only changes if we change our measurement of rotation, which we will do tomorrow. All right, so we have to decide whether we're going to use sine or cosine or what. So we could use cosine and make it negative because it starts at the bottom. So we could try that. So we could go, let's do that one first. So H is negative, so vertical reflection of amplitude 1 cosine theta. If we use negative cosine, we don't need a phase shift. Plus 2. So that'd be a solution. Or we could use, say, sine. Sine would line up. It would here, so we'd have to have moved it 90 degrees to the right. So we can try use that one. So that would be a positive sine. So just 1 sine theta right 90 degrees would be minus 90 degrees, plus 2 as well. And there's a bunch of other answers. So we could make this a cosine that's been translated right 180 degrees. We could make this we could graph some stuff over here and find ways to translate it left. And there's infinitely many solutions. But these are probably the two most common, simplest ones to find. Okay. All right, so that's it for our lesson today.